We begin today's lesson with an area problem. So you are asked to determine the area between the curves g of x and h of x. So please make certain you've completed your lesson preview before I discuss the answers. So as you began this problem, there are a couple things I wanted to remind you of. You should draw a picture whenever working on an area or a volume problem. This is also not a calculator problem, so you should not be using a calculator unless directed to use one. The area equation should be written very carefully. So we take the top function, which is your g of x, and we're going to subtract the bottom function, h of x, because area is found when we look for the height, which would be your g of x minus h of x in this problem. So we have area equals our integral. Now this would not be counted for full credit. We need to have our parentheses written correctly. The height is your e of x plus your tangent of x, and the thickness of a rectangle, if we were to think of Riemann sums, would be your dx or your delta x. Now this problem was chosen specifically because I wanted to remind you of two integration techniques. One is your u substitution. In this particular problem, we know the antiderivative of e to the u, but we do not know the antiderivative of e to the 2x. So we're going to let u equal 2x, in which case du is going to be 2 dx if we have differentials. Now, we can use substitution du over 2 is equal to dx in order to rewrite this problem. As you'll recall, the endpoints are x values, so you will have to change those into u values if we are going to use them. So we'll have the endpoints are now 0 to pi over 2 e to the u du. Once you substitute du over 2 in for your dx. So when we integrate, we now have e to the u over 2 evaluated from 0 to pi over 2. Now there are other ways to integrate this particular function, but that's the way I wanted to demonstrate today. The tangent of 2x. Do you know the antiderivative of the tangent? I don't think so. If you do, that's great. If not, you're going to have to use your trig identities in order to rewrite this problem. You might rewrite it as sine of x over the cosine of x dx. Once you do that, you're ready to use u substitution for the second part. U is equal to the cosine of x dx. Du is going to be equal to the negative sine of x dx. Again, you can solve for dx and do some substitutions to rewrite your problem. Now you need to take care of these ideas. I want you to be reminded of u substitution, the way to rewrite problems in terms of area, and once again, to always draw pictures when you're solving area and volume problems. And next, we will talk about your course review. So it's important to me that you look at the syllabus. So the syllabus has been uploaded for you in Schoology. So please read the syllabus, understand how you're going to be graded and what is expected of you throughout this course. You also have some technology that needs to be prepped. For example, you might need to download CamScanner so that you can upload all your files as one PDF file whenever you do a submission. Also, you will need to sign up for AP Classroom. That information is also found in Schoology. So for today's lesson, we're going to review area, but I'm not as interested in the process as I'm interested in these formulas. As we look at the formula for area, you're very familiar with this. You've already had a course in AB Calculus. So you're very good at finding the area between two curves, but I want you to really understand how it's working. When we are using the differential dx, that means all of your heights are cut perpendicular to that x-axis. We are drawing rectangles cut perpendicular to the x-axis. Now, as I look at a rectangle, the area of the rectangle is going to be the height of the rectangle multiplied by the width of the rectangle, and each rectangle is going to be a width of delta x. Now, if I take a multitude of rectangles and I were to think about the limit of all of these areas, one area was going to be f at some values, let's call that c sub k, minus g of c sub k, some values. So this is the height of one rectangle. And if we take that height and we multiply it by delta x, which is the width of one rectangle, and that delta x is for each individual rectangle. So I'm going to write it as delta x sub k. And I take the sum of each one of these rectangles where k is equal to 1 to a certain number n, and I don't know what they are. And we take the limit as each one of these rectangles the width gets smaller and smaller. Wait a minute, if we do the limit with the widths getting smaller and smaller, that's your delta x is going to 0. So as we do this, this is actually the definition of an integral. We're going to take the sum as your k equals 1 to infinity of the heights. Well, the heights, again, are going to be some sort of f of ck minus g of ck multiplied by each of these little delta x's, and that is going to be the definition of an integral from a to b, where a and b are going to be the limits that we're going to integrate between of our f of x minus g of x, or the top minus bottom of each one of these heights, and multiplied by dx. So this is how we get the definition of an area problem from the infinite number of rectangles into an integral. Now, if we think in a similar way, this time we're going to cut on the y-axis for each one of these rectangles. The width then becomes a delta y. So the width of each of the rectangles is delta y. And then again, if we take the sum for n equals 1 to infinity for each of those heights multiplied by delta y, we will end up with the formula for the area when we cut on the y-axis. So these ideas were very important last year, and you're going to practice a little bit more finding the area between two curves. Now, leading into today's lesson, you need to be able to explain the calculus using geometry and limits behind the disk washer method, so that we can find the volume of a solid of revolution spinning about the horizontal axis. Next, you're going to explain the calculus behind the shell method. Your third objective is to explain the calculus behind cross-sectional volume. Now, all three of these concepts are ones that you have had practice with in your last course, but did you understand where the formulas come from? That is our goal today, to understand the formulas and where they come from. So go ahead and explain these three concepts. Afterwards, you can continue with the video. So you've thought about the calculus behind the disk washer method. Essentially, to estimate a volume, we're going to slice a rotated region into these thin circular disks. And we're going to take the volume of each of these disks, so that your volume is going to be the area, which is pi r squared for the radius of each disk, multiplied by the thickness, which is going to be your delta x sub k. So the volume of each slice can be given by an area formula multiplied by the thickness. Now, as the thickness goes to an infinitely small amount, if we were to add each of these different slices of volume, there's our pi r squared k, delta x of k, where k is equal to 1 and n. Now, as your delta x's go to 0, n is going to infinity. And that is the definition of an integral, where if we take the limit as n goes to infinity for the sum, we're going to have pi r of x quantity squared. Now we're cutting on the x-axis. So each of these x's are delta x because it's perpendicular to the x-axis. So your delta x is equal to dx as we go to infinity. And we use our lower limit a, upper limit b to tell us what we're going to be rotating for which x values. As we look at the calculus behind the shell methods, it's very similar. Once again, we're going to find the individual volume. Now, the volume, again, is going to be area, and the area, as it's being wrapped around in this particular problem, around the y-axis. So we're going to spin on the y-axis, but the shells that we're creating are all going to be a thickness of delta x as they're being spun. So we spin on the y-axis, but we're going to use x values when we think about our volume equation. So the volume, again, for one little shell is going to be the area, which is 2 pi, the radius with respect to the value that we're looking at with x, and then the height at which we're looking at as well. So that's our area, but then we have to multiply it by the thickness of each one of our shells, which is a rectangular shape, so that we then will have the volume of one shell in particular. Again, if we take the limit as your n goes to infinity for the sum, k equals 1 to n of your area, which is your 2 pi r k h k, multiplied by the thickness of each shell, then we will have an integral that will represent volume. And this integral is being spun from x equals a to x equals b. Here's your 2 pi. R is a function of x. H is a function of x, and dx. But let's look at this picture a little bit more carefully. We're spinning on the y-axis. The radius is going to be some sort of function of x. Now the radius is perpendicular to the height. So the height is once again top minus bottom, and the radius is often x unless we move the axis of rotation. Next, let's consider the calculus behind cross-sectional volume. So for cross-sectional volume, your shapes can take on semicircles, squares, triangles, whatever you are asked to find in terms of the cross-sections. Essentially what's happening is you're given a function that we're going to build through cross-sections, a volume that comes up off the base of the function and into the z-axis. Now, in order to find the area of each one of these shapes, we know that the integral is actually the area, a of x, multiplied by the thickness of each shape, which is dx. So we've been practicing that from a to b. Now, as we look at cross-sectional volume, the area is given to you by particular shapes. In this particular picture, you see that the area is a semicircle. Semicircle is 1/2 pi r squared in terms of what we know for the formula of a semicircle. Now, as you look at your picture, notice that the line that is drawn from the x-axis, so we are cutting on x, delta x is what we're using again for the volume, and we want to have the function written with respect to x. Now, unfortunately, as you can see, the way this is drawn, it is a y value that's is the diameter of this particular picture. So we know that the area is 1/2 pi, but it's not the radius, it's the diameter. So we're going to take the y value and cut it in half squared. Now that's for each and every single one of the slices. Let's simplify this area formula. We have 1/8 pi y squared, but we know that y is equal to negative x squared over 10 plus 11. So we can solve for y squared. Y squared with respect to x is negative x squared over 10 plus 11, and that's going to be squared. So the area with respect to x is, here's our 1/8 pi. Y is replaced now with negative x squared over 10 plus 11. Here's going to be a squared, and that will be our area formula. Now, once again, we want the volume. Volume is going to be the integral of the area from the lowest value to the highest value. It looks like we're going from -10 to 10. And then all the slices are going to have an area of 1/8 pi and our -x² over 10 plus 11 quantity squared, with the thickness of each being dx because we're cutting on the x-axis. If we cut on the y-axis, of course, the thickness will be dy, and you're going to have to reevaluate the entire problem. The second question I have here is done very similarly, except this time the area is given to you in terms of rectangles or squares. It looks like these are supposed to be squares. So we know that the area of a square is s squared. These again are cut on the x-axis. But as you look, the heights that are given to you in terms of the y value. So in this problem, we have again the area is y squared. I need to have the area with respect to x because we're cutting on the x-axis. Substitute in what the y squared is equivalent to for this expression, and then you'll be able to write your volume formula. All right, so these are ideas for the lesson practice. Hopefully you came up with similar ones. What I'd like you to really think about right now is how would you find the length of a curve using the ideas presented in questions 1 and 2 in order to find the length from x squared from x equals 0 to 3. Give that some good thought afterwards. Practice with the lesson follow-up. This part of the video is going to review question 18, just as a reminder for students who may have forgotten some of their AB calculus materials. When we are going to find the volume, we need to first graph the function. And you should graph the function for each and every problem. So we have the square root of x, y equals 2. So we have a horizontal line at y equals 2, and x equals 0. So you can see that the bounded region is trapped between those three curves. We're spinning about the x-axis. Draw where you are spinning. Drawing where you're spinning is important because we want to figure out the axis of revolution. The axis of revolution in this problem, let's think here. We are spinning about the x-axis. As we take a look, it seems as if we were to use a larger radius, r of x, and a smaller radius, little r of x. Those are going to be easy to identify. So we know that spin x, use x, that's going to be the formula pi r squared when we set up our problem. So the radius with respect to x is going to be 2. The little radius with respect to x is going to be the square root of x. Following that, we know that the volume is going to equal pi, the integral, we'll get the endpoints in just a moment. Then we have big R squared, so there's your 2 squared minus the square root of x squared. Now these parentheses were not drawn correctly. You have to put parentheses around the entire expression, then dx. Now the endpoints are your smallest x value and your largest x value. The largest x value occurs when y is equal to 2, so that will give us the x is 4. So we're going to integrate from 0 to 4 because the x's have to match the integrations. Dx is going to have to be x values as your endpoints, and then you will solve that. For question B, we need a whole new picture because we have a different axis of revolution, and the axis is key to figuring out what's going on here. So we begin by drawing the square root of x. We want to draw y equals 2, and we know that we have x equals 0. The region is bounded by those 3 different curves. We draw where we're going to spin. We're spinning on the line y equals 2. Now, y equals 2 is parallel to the x-axis, so we're going to spin x. Once again, let's try to use x. We spin x, use x, draw the radius. The radius comes from where you are spinning to the outer edge. Notice this one doesn't have a hollow region, but the radius with respect to x is going to be a top minus bottom, so that's going to be 2 minus root x. We do not have an inner radius, so just one x value. Spin x, use x is going to be pi r squared, so we now know that the volume is going to be equal to pi. The integral, we've already established that our endpoints are x values, so we're going to 0 to 4. And then we have the quantity 2 minus root x. That's going to be squared dx. And then you multiply it out in order to integrate. For part C, we are going to again draw our picture. When we draw it, we have the graph y equals square root of x. We'll have the y equals 2, x equals 0. Here is our region. Now, for question C, we are spinning about the y-axis. So again, draw where you are spinning. The reason we want to do that is we want to set in place how to solve the problem. So we're going to spin about the y-axis, but we still want to cut on the x-axis. So spin y, use x, which is 2 pi rh as the area formula we're going to use. The radius is drawn from where we are spinning to some arbitrary point. That value is going to be x comma y. So the radius for which we're spinning is equal to x. So the radius with respect to x is x. Now your height is always drawn perpendicular to the radius. So the height with respect to x is a top minus bottom in this case, the top function being 2, the bottom function being square root of x. So now we have all the different components to write our volume. So volume is equal to 2 pi integral, and then we want to have the radius, which is x, times our 2 minus root x dx. And the x values have to be part of the endpoint, so we want to go from 0 all the way to x is 4. So that'll be the limit. So these must match. This is equal to x, whatever you have that you're cutting on your axis. So for question D, we're going to do something similar. We're going to draw the picture. When we draw it, we have our square root of x. We'll have our y equals 2 and our x equals 0. So again, the same region, but this time we are spinning about the line x equals -1, which is way over here. So this is x equals -1. So draw your spinning axis, and you can see this time it's parallel to the y-axis. So the ideas you want to use are spin y. I'm going to use x again. Spin y, use x, which tells me we'll follow the formula 2 pi rh. So we figure out your radius. So the radius is going from our axis of revolution to some arbitrary point. We know that arbitrary point is xy. Now, for those of you who have maybe forgotten, the distance is x from your axis, your main axis of your x equals 0, and then we have a distance of -1. So if we do right minus left, it's going to be x minus -1 is equal to the radius. And then the height, once again, is always perpendicular to the radius. So the height in this problem is going to be top minus bottom, or we're going to have 2 minus root x is the height with respect to x. So the volume is going to be 2 pi integral from the radius, which is x plus 1 this time, since we shifted the axis of revolution, times the height, which is 2 minus root x. Here's our dx, and we're going to go from 0 to 4 because those are the x values for our endpoints. All right, so this was just a brief overview of determining volume spinning on different axes. For our last slide, we're going to find the volume of a solid that's created when we build cross sections perpendicular to the x-axis. Now, these cross sections that we build are going to be semicircles. So if we draw what's expected, we have a semicircle coming up and out on each one of these different values, and they will be three-dimensional as they come upward. With that in mind, we know that the volume is going to be equal to the integral cutting on the x-axis. So we're going to use x values, a, b, dx. We're going to stack all of those little areas together, so we will have the area with respect to x. So I need to find the area of a semicircle, and that area is 1/2 pi r squared. Now 1/2 pi r squared. We need to find then the radius of each one of these semicircles. Now the radius is 1/2 of your diameter. So radius is 1/2 of the diameter of a semicircle, but the diameter is going to be given to us through the y value. So our area is 1/2 pi take your y value, cut it in half, and square it. So simplify this expression. We now have 1/8 pi y squared. But as you can see, I wanted the area cut with respect to the x-axis because each of these is dx in terms of the thickness for each semicircle. However, we were given this information. Y is equal to the square root of 25 minus x squared. So y squared must be 25 minus x squared. Substitute that information in. We have our 1/8 pi times the quantity 25 minus x squared. And now we have the area with respect to x. Ready to use our formula. The volume then is going to be equal to the integral, I'll come up with my endpoints in a minute, of 1/8 pi times the quantity 25 minus x squared. Here's my dx, the endpoints for the x values. Now, as you can see, just from the picture, we're going to go from -5 to 5, but if you weren't certain, you would take your square root 25 minus x squared and set it equal to 0. Afterwards, integrate and you have the volume.